So I think what we should do now is do the resynthesis in a better way. And the way that we're going to do that is we're going to use the magnitudes that we create to make masks. And then those masks are going to mask the FFT magnitudes or the STFT magnitudes from the original in such a way that those masks are going to only sort of let through the mask certain parts of the original STFT spectrogram. So the way that we're going to do that is we'll leave this as is, and we'll say resynthesis without masks. And then we'll do another one where we do resynthesis with masks. So the first thing we're going to do is we're going to get all of these resynthesized magnitudes. We actually want to get them into an array. So I'll say something like, so that we can get them basically stacked on top of each other. So now we'll have this list, here we're using 3 components. We'll have 3 elements in this list, and each one will be a different result of this resynthesis process here. Resynthesized mags equals a numpy array. So now we have it as a numpy array. And just to sort of keep track of everything, but I want it to be stacked because they're sort of stacked on top of each other in that list. What we want to do is we're going to take all of those different components that are stacked together and we're going to sum them into one. So it's like if we took each one of those STFT magnitude matrices and added them all up, we'd get that summed matrix. And we can do that by saying np.sum the resynthesized magnitudes, and we're going to say along axis 0, which means that it's going to take all of the elements in that first top layer, axis 0, and sum them all together. And we'll see what happens when we print this here. So then we'll do a print. Great, that's what I want. Okay, so now let's run it. Input and components. Okay, so there's our decomposition. So that's still looking good. Our bases looks like this. Our activations looks like this. Our stack looks like this. So we have 3 elements. Those are our 3 components. And then each one of those elements is a matrix that is 513 values tall by 887 values long. And these 513 values are our STFT or FFT magnitudes, and the 887 are each one of our windows that were analyzed with the FFT. So that's our sort of time dimension, is the 887 FFT windows there. And then when we sum them together, right, we're adding these 3 matrices together on top of each other, element-wise, just each position in the matrix gets added to the same position in the other matrices. And so then we'll have a matrix that looks like this. And so this is our summed matrix. So now what we want to do is we're actually going to take 1 divided by this matrix. And what it's going to give us when we multiply this multiplier matrix against each of the resynthesized magnitude matrices is what's called the softmask. And what this means is that for any given point in our spectral space, a time, frequency, position, if we were to sum up the value at that spot in all 3 masks, they would sum to 1. And using a softmask here is nice because it sort of blends all of these 3 different components together in a pleasing way. And it's also great because then when we multiply the masks by the original magnitudes from our STFT, we know that each position in the matrix is essentially going to be multiplied by 1 because it's being multiplied by all of these masks, which sum to 1. So we know that we're going to get all the energy from the original STFT to come through the masks. But essentially, each part of the original STFT will only go through one of those masks, which is how the energy from different parts of the original STFT ends up in the different components. So we're going to take our summed magnitudes. That's great. We have those summed up. I'm going to do one more thing here, which is I'm going to say np.maximum. And I'm going to put in a little epsilon here. Let's just say 0. Yeah, great. That looks good. Because since we're going to do 1 divided by that, we want to make sure that we are not accidentally going to divide by 0 anywhere. So we'll just say if the value in this array, which it probably won't be, but if it were smaller than this, like such as being 0, change it to this, just to make sure you don't divide by 0. Okay. This is no longer summed megs because now we're checking against this small value, sometimes called an epsilon. So we're taking the maximum with the epsilon, and then we're doing 1 over that. And so this actually becomes our multiplier. Resynthesized megs, let's call it masks, equals the resynthesized megs times the multiplier. And actually, what we're going to do next is we're going to take these masks. We'll now have still 3 of them stacked up in that way. We can also just say times megs, which are our original magnitudes. And now these will be our, let's call it resynthesized megs with mask. Very verbose wording here. Okay, so then what we can do is we can use these magnitudes to combine with our phases and resynthesize them into audio. We've already done that, right here like this. So if we have a magnitude, we just need to do this to it, the rest of this. So 4 megs in resynthesized megs with mask. Let's see if this gets it right. We'll combine, actually let's call it, we don't want to call it megs because we already have something called megs. Let's call it megs with masked megs. Okay, so we take those, we multiply them by the complex number that we derive from these phases, and then we do the inverse STFT with our resynthesized STFT. Hop lengths is there, and we write it to here. Okay, resynthesized with mask. Look at that. Thank you, Copilot. Okay, so now let's run this. And then let's go listen. Cool, although it only did 1 of them. Doesn't make any sense. And now we should get all 3. Ooh, it did kick out the ring of the snare there, so we'll get 1. That's the kick and the hi-hat together. That's so good. And there's the smack of the snare, but if we run it again, this one looks more likely what we tend to get. There's just the hi-hat, just the kick, and just the snare. Cool. Great. Oh, you know what I just realized? I think that's not what we're trying to plot there. We're trying to plot the original magnitudes. But here, when we do this plot, masked megs. Okay, yes. So it's thinking that I'm trying to do that, which I'm not. I actually still want to just plot the megs, which is our original megs. It's changing it all on me. Okay. So the original megs should be that. Here we'll use the original megs for our decomposition. And then when we do the masking, we want to multiply them by the original megs. Yeah. And then down here, it will, again, be the original megs. Okay. It's better, right? So what we were seeing, rather than seeing the original magnitude spectrogram from the original STFT, we were actually seeing just 1 of the masked magnitudes from our decomposition and mask creating process. Okay. So this masking business, this is how the Flucoma NMF objects sound so good, essentially, is that they're using the original magnitudes of the original STFT to create the resynthesized components. But it's masking those magnitudes by a soft mask. What parts of the original STFT should we let through to be our snare component? And what parts of the original STFT should we attenuate to create the snare component? And same for the other components. And so that's why it sounds so good. And again, we can just notice the difference here. Here's without that masking. Here's just the resynthesized component by taking the activation and basis and doing the outer product. So we get a new matrix out of them. So, not bad, but this is the cleaner and clearer. Here's the hi-hat without the original magnitudes. You can hear that sort of crunchy, stuttery spectral thing there when the symbol is supposed to be sustaining. Here's the hi-hat one. That's without the original magnitudes being masked. Here's with the masking strategy. The kick to me just sounds a little more round, a little more full, a little more natural.